Welcome everyone. Today, we'll discuss the importance of cathodic protection in preventing metal corrosion and extending the lifespan of critical infrastructure. Corrosion is a major challenge in industries like oil, gas, and water, and CP is a proven solution to mitigate these risks. Before diving into the details, let's understand what cathodic protection is and why it matters. CP is a technique used to control corrosion on metal surfaces by making them act as cathodes in an electrochemical cell. Corrosion is a natural electrochemical process that deteriorates metals when exposed to moisture, oxygen, and other environmental factors. It leads to structural weakness, safety hazards, and costly repairs, especially in pipelines, storage tanks, and marine structures. Cathodic protection, CP, is a proven technique to mitigate corrosion by converting the protected metal surface into a cathode of an electrochemical cell. This is achieved by supplying electrons to the metal, preventing oxidation reactions that cause corrosion. CP is widely used in industries such as oil and gas, water distribution, and marine engineering because it significantly extends the lifespan of assets, reduces maintenance costs, and ensures operational safety. Understanding CP is essential for engineers and asset managers to maintain infrastructure integrity and comply with regulatory standards. The importance of CP lies not only in corrosion prevention but also in its role in sustainability, as it minimizes resource wastage and environmental risks associated with leaks or failures. Sacrificial anode systems, cathodic protection principle and applications. Sacrificial anode cathodic protection systems operate on the principle of galvanic corrosion, where a more reactive metal, anode, corrodes preferentially to protect the structure. Common anode materials include zinc, magnesium, and aluminum, chosen based on environmental conditions and required protection levels. These systems are simple, cost-effective, and do not require an external power source, making them ideal for remote or submerged applications such as offshore platforms, ship hulls, and underground pipelines. The anode sacrifices itself by releasing electrons to the protected metal, thus preventing its oxidation. Design considerations include soil resistivity, electrolyte composition, and expected service life of the anodes. While sacrificial systems are easy to install and maintain, they have limitations in high resistivity environments and for large structures where current demand exceeds anode capacity. Engineers must calculate the number and placement of anodes to ensure uniform protection and avoid underprotected zones. Impressed current CP systems working mechanism and advantages. Impressed current cathodic protection, ICCP, systems use an external DC power source to supply current to inert anodes, such as graphite, mixed metal oxide, or titanium. Unlike sacrificial systems, ICCP can deliver higher and controlled current outputs, making it suitable for large structures like long pipelines, storage tanks, and marine vessels. The system consists of a rectifier, anodes, and cables, allowing precise adjustment of protective current based on environmental conditions and structure requirements. ICCP offers advantages such as longer service life, reduced maintenance, and adaptability to varying soil or water resistivity. However, it requires continuous power supply, monitoring, and higher initial investment compared to sacrificial systems. Proper design ensures uniform current distribution and prevents overprotection, which can damage coatings or generate hydrogen embrittlement. ICCP is widely adopted in critical infrastructure projects where reliability and long-term protection are paramount. Current distribution in CP systems, challenges and mitigation strategies. Current distribution in CP systems is influenced by factors such as soil resistivity, coating quality, and structural geometry. Uneven distribution can lead to underprotected areas, accelerating localized corrosion. Interference issues occur when CP systems interact with nearby metallic structures or electrical systems, causing stray currents that may damage adjacent assets. Common interference scenarios include pipelines crossing rail tracks or sharing corridors with other utilities. Mitigation strategies involve careful design, isolation joints, and periodic monitoring to detect and correct anomalies. Engineers use modeling tools and field measurements to optimize anode placement and current output. Addressing interference is critical for regulatory compliance and preventing costly failures. Advanced techniques like decoupling devices and grounding systems are employed to manage stray currents effectively. Understanding these challenges ensures CP systems deliver consistent protection without unintended consequences. Performance assessment, maintenance and monitoring CP systems for buried pipelines. Monitoring is essential for long-term protection. Monitoring the performance of CP systems is essential to ensure long-term protection of buried pipelines. Techniques include measuring pipe-to-soil potential using reference electrodes, conducting close-interval surveys, and performing current and voltage checks at test stations. These assessments help verify compliance with protection criteria, such as maintaining potentials more negative than -850 MV versus a copper/copper sulfate electrode. Regular monitoring detects coating defects, anode depletion, and interference issues early, allowing timely corrective actions. Advanced monitoring systems use remote sensors and data analytics for real-time performance tracking, reducing manual inspections and improving reliability. Maintenance activities include replacing depleted anodes, adjusting rectifier settings, and repairing damaged cables. Effective monitoring not only prolongs pipeline life but also ensures safety, environmental protection, and adherence to industry standards like NACE SP0169. A proactive approach to monitoring minimizes operational risks and optimizes lifecycle costs. Finally, CP design and maintenance are guided by standards. Here's key standards and literature. References for cathodic protection include industry standards, technical papers, and guidelines that provide best practices for design, installation, and maintenance. Key references include NACE international standards such as SP0169 for control of external corrosion on underground or submerged metallic piping systems, ISO 15589 for pipeline CP systems, and API RP 1632 for cathodic protection of underground petroleum storage tanks. Additional resources include textbooks on corrosion engineering, research articles on CP performance, and manufacturer manuals for CP equipment. These references serve as authoritative sources for engineers and technicians to ensure compliance, optimize system design, and stay updated with technological advancements in corrosion prevention.